When the TSG was started off by John Ramsay and Robert Nicholson in 1970, the main focus of research was strain and its expression through geological structures such as folds and shear zones. This was the first thematic area to be associated with the TSG. The theory and measurement methods of finite strain were largely already established. Cleavage was recognized as forming parallel to the principal flattening plane of the finite strain ellipsoid, and therefore through its orientation and its intensity it mapped out strain trajectories from local to regional scales. Techniques were focused around recognizing and measuring objects of known original shape such as ooids and deformed conglomerates, stretched belemnites and reduction spots in slates illustrated here, and evidently flattened in the plane of the cleavage. This image shows how foliation can be defined by clusters of flattened objects and how heterogeneous strain is reflected in the shape and orientation of objects and by the intensity of the schistosity. We will come back to strain in the context of rock mechanics, but we can recognize two approaches to rock mechanics: applied or geotechnical rock mechanics and geologically oriented rock mechanics. From the point of view of the TSG, the latter has been the main focus. As well as hundreds of individual contributions, the TSG has badged a great many meetings featuring rock mechanics and microstructures, such as on shear zones, on electron microscopy, pressure solution, geomechanics applied to geology, and the geomechanics of shales. The arrogant polymath Henry Clifton Sorby in the mid-19th century made outstanding advances in the observation and description of the deformation of rocks and metals, employing the optical microscope for the first time. His studies included recognizing what we now call pressure solution, illustrated with the two images on the bottom left here, and the spectacular microstructures that it produces. 80 years later, David Griggs started quantitative rock mechanics in the 1930s, applying the high-pressure techniques of P.W. Bridgman, and he expected to find that his experiments would produce flow by pressure solution. The pair of them would likely have suited each other in temperament. I gave a seminar in 1972 at UCLA with Griggs attending, and I was astonished by the aggressive and dismissive questioning he employed afterwards. He was a hard man, and I would have a number of quite bad words to say about him. After the Second World War, Griggs and his co-workers focused on Yule marble and discovered that rocks could flow like metals by intracrystalline plasticity. But he quickly realized that the attainable combinations of pressure and temperature would not allow framework silicates to be deformed experimentally with equipment available at the time. Very high pressures would be needed to suppress dilatant cataclasis to allow plastic flow stresses to be attained at temperatures less than 1000 Celsius. Griggs and Blasek designed the solid medium machine that could apply 1.5 gigapascals to allow silicate deformation at 800 to 1000 degrees Celsius. In this way they discovered hydrolytic weakening of quartz and other silicates. I remember a room being filled with more than a dozen of these machines at UCLA. These machines have led to a large amount of advance in understanding silicate deformation, including the deformation of granites and granitoids, which was focused upon over many years by Jan Tullis. In the meantime, Mervyn Patterson in Australia developed and refined the use of gas medium machines to allow very high temperatures, 1200 degrees Celsius and higher, limited only by the melting of the minerals concerned or their chemical breakdown, and this would allow flow stresses to be reduced sufficiently so that more moderate pressures could prevent deformation being dominated by cataclasis. By 1990, he went into commercial production together with Anutech, which is the commercial arm of the Australian National University. And the first such Patterson machine was installed in Manchester in 1990. and now there are about 13 of these game-changing machines installed worldwide. In the 1960s, Hugh Hurd at UCLA carried out the first systematic studies of the effect of large changes in strain rate on rock deformation. This is necessary to obtain constitutive flow laws. The formulation on this slide shows that the slow rates of natural rock deformation at moderate temperatures can be traded for faster deformation at higher temperatures. The multiplication between functions of the independent variables means that the relationship between strain rate and any one of the independent variables can be studied whilst keeping the others constant. The graphic shows how stress-strain rate relationships can be determined whilst keeping the temperature constant. In this way, we can build up the constant terms in the constitutive flow law. One way graphically to represent constitutive flow laws was by deformation mechanism maps. These are the rock mechanics equivalent of a phase diagram. This representation was introduced by material scientist Mike Ashby. Some of the very first of these for rocks, for example calcite and quartz, were presented at TSG meetings in the 1970s. Constitutive laws are needed to infer the strength of the lithosphere as a function of depth. At shallow depths, deformation is dilatant and therefore pressure sensitive and involves faulting and cataclasis. In 1967, Jim Byerly, who worked at the US Geological Survey, suggested that the resistance to frictional sliding is largely independent of rock type. This is a very useful generalization that has stood the test of time, illustrated in the diagram in the top left. This leads to the idea that there is a mid-crustal mechanism transition from faulting to flow, with strength at greater depths falling off because of the sensitivity of plastic flow to temperature. This was demonstrated directly for calcite rocks along a specified barothermal gradient shown here in the middle diagram. If we include the effect of a crude mineralogical stratification of the lithosphere, this leads to the concept of a rheological stratification of the lithosphere. Plate boundary rupture requires the stress state to spread over the whole of the strength profile. Through the 1980s, it became clear that, like metals and ceramics, rocks at high temperatures could display grain size sensitive flow, in which grain boundary sliding is accommodated by some combination of intracrystalline plasticity and solid-state diffusion. In this regime, one can trade strain rate for grain refinement. For experiments, grains must be made very fine. Grain shape does not evolve with strain. Surface energy and diffusion keeps the grains equidimensional. And for experimental studies, it is necessary to fabricate synthetic samples of controlled ultrafine grain size. In the illustration on this slide, we have calcite and quartz. The top left diagram here shows a surface of calcite grains, very fine calcite grains, which have been heat treated but not deformed. And to the right of that, you see what happens after deformation by grain size sensitive flow. The grains have been sliding out of the surface, one with respect to the other, indicating the nature of the deformation. In the slide beneath that, we can see that after quite a large strain, the grains remain equidimensional, and the true strain is indicated by the deformation of this large embedded grain, which has been stretched out by a factor of 10 relative to its original grain size. The picture on the right shows synthetic ultrafine grain quartz, which also can be made to deform by grain size sensitive flow. Determining constitutive laws requires accurate stress measurements, hence smaller strains to ensure homogeneous deformation. But natural strains can be far larger, and it's clear that microstructure and petrofabric evolve with strain, hence flow stress is likely to do so too. There was an imperative to find ways of doing rock mechanics to high strains, that is, involving grain shape factors of 10 to 1 or more. In compression tests, this can be achieved at the expense of large strain gradients and heterogeneous deformation as the specimen wraps itself around the loading pistons. But Mervyn Patterson added a deformation in torsion capability to his machines to allow high strain tests in simple shear. Also, plastic deformation in extension can allow advantage to be taken of geometric localization instability to produce very high but locally homogeneous strains. On the left are some examples of experimental high plastic strains accompanied by dynamic recrystallization and grain size reduction in calcite and in olivine. At this first mention of olivine, it should be mentioned the outstanding contributions of the Minnesota group, led by Dave Kolstedt on the right, to establish flow laws for intracrystalline plastic and grain size sensitive flows in olivine, the influence of small amounts of melt on deformation, and the extraction of basalt melt from its mantle protolith. However, this is not to say that no other groups have worked on olivine. Many have, and have produced very substantial advances. Mother Nature gives us microstructures and petrofabrics, but experiments give us all of these things, but mechanical data as well. Identical microstructures are used to justify the application of mechanical laws to natural deformation. The 1970s onwards saw the application of transmission electron microscopy to rock deformation, both natural and experimental, with many presentations on this theme being made at TSG meetings. Towards the end of that decade, compositional or Z-contrast backscattered electron imagery in the scanning electron microscope began to feature more and more, complementing optical imaging. Understanding deformation in micas has always been difficult. A recent application of high-resolution transmission electron microscopy by the Liverpool group, illustrated here, has revealed what they call rip locations, like dilatant propagatable rocks in a carpet, as a means of propagating plastic slip along the basal planes of micas. For a period of 40 years, Jeff Lloyd has made a series of outstanding contributions on the microstructure and petrofabrics at TSG meetings. He was in the vanguard of the development and application of electron backscatter diffraction imaging when he and Colin Ferguson stuck images of electron channeling patterns of single crystal quartz in different orientations onto a sphere to show how they could be used to determine the orientation of crystallites in the SEM. Since then, EBSD has been extensively applied to the determination of petrofabrics in naturally and experimentally deformed rocks, and to study in detail the rotations that are produced during plastic deformation and recrystallization. This example is from a recent study of high-strain olivine deformation in axisymmetric extension. Modeling can be used to predict petrofabric evolution during deformation along particular strain paths, and it can be verified via experimental studies. In 1976, Gordon Lister arrived from Australia to the Exeter Tectonic Studies Group meeting to describe the computer simulation of quartz fabric development using the Taylor-Bishop-Hill approach, which assumes a homogeneous strain. There have been other more relaxed developments of that concept subsequently. As the Flynn diagram figure shows on the right, each specific strain path produces its own fabric evolution type, and this intensifies with strain magnitude. These inverse pole figures show the same approach applied to axisymmetric shortening of calcite aggregates, and how the same fabric type can be produced in experiments as is produced in the modeling studies as well. Thus far we have focused only on high temperature flows, but in the past 30 years or so brittle deformation has enjoyed a renaissance. Through the 1980s, the role of porosity in promoting ductile flow through permitting volumetric compaction during deformation became apparent. This results in a negative slope, on the right of this diagram, of the yield envelope, whereas dilatancy that accompanies cataclasis at lower pressures has a positive slope and results in localization of deformation as brittle faults. In a further manifestation of the Byerlee frictional generalization, this type of normalized yield surface for a wide range of rock types deformed in this way tends to be approximately independent of rock type. As with plastic deformation, it was progressively realized that a small displacement test could not adequately characterize the development of fault strength and microstructures. And whilst for incipient faulting, lab-determined friction seems to fit with nature, this is often not true for big faults with large displacements. Ring shear apparatus had long been used in geotechnics and in soil mechanics to produce large finite displacements, but beefier machines with larger displacement and rate capabilities were clearly needed to understand seismicity and the evolution of frictional properties in rocks at greater depths. Several machines have been developed for tectonophysical applications, such as the Shiva machine here in Rome. The figure on the right generalizes the way that large slips and high rates typically result in a dramatic decrease of friction coefficient for a variety of different reasons. These can include dehydration reactions, raising the pore pressure, frictional melting, generation of ultrafine fragmentation, or formation of weak reaction products such as graphite or talc, removal of asperities from the fault surface, and the alignment of phyllosilicates. The final two slides focus on some outstanding issues and new and ongoing developments. We still have the outstanding problem of understanding induced seismicity and the prediction of natural seismicity. In the case of high temperature rock deformation, there will need to be some increased focus on accompanying chemical changes. Despite the work that has been done in this field, we've barely begun to scratch the surface here. Then there's the possibility for new developments in the combination of techniques of imaging with in situ deformation. For example, observations using transmission electron microscopy, scanning electron microscopy, synchrotron X-rays, neutron diffraction, all of these during deformation at high temperature and pressure. Finally, attacking pressing societal issues will require greater convergence of engineering rock mechanics with geological rock mechanics and petrophysics, as engineering gets deeper in the earth and evolves in different ways to traditional oil and gas. Thank you for listening.